Good afternoon. Wonderful. Good afternoon, everyone, and welcome to the 20th Annual Goldstick Family Lecture in the Study of Communication Disorders, made possible by the generosity of Philip and the late Beverly Goldstick. I'm Cristala Musa, Dean of the College of Education at Illinois. The last couple of years, I've said I'm the new dean, but I guess I'm not that new anymore, so they took the new out. It's wonderful to see so many students and faculty members here today from special education, speech and hearing sciences, engineering, and other units from across campus. Additionally, we welcome our community members and practitioners and our online attendees to this event, joining us from across the nation. We're really excited today to hear from a leading scholar doing important work at the intersection of technology, specifically AI, and communication disorders. So our 20th annual Goldstick lecturer is Dr. James Rehg, joining us from right here at the University of Illinois Urbana-Champaign. However, he's actually new to our campus. So it's a wonderful opportunity for him to see this side of work that we're doing in education. Dr. Rehg is the founder professor of computer science and industrial and enterprise systems and professor in the Siebel School of Computing and Data Science in the Granger College of Engineering. The title of his talk is Leveraging AI to Measure and Model Social Behavior. The College of Education is at the forefront of efforts to identify ways of leveraging technology and AI specifically to support the unique needs of learners across ability levels and the age spectrum. In collaboration with units across campus, we have actively participated in conversations and dialogues on the role of AI in learning. And as a result, Dr. Rehg's lecture this year is particularly timely. It's of course timely for a whole range of reasons. I think anyone who has not heard the word AI, this year probably doesn't exist. So we're very excited to have this opportunity to bring his expertise to this timely and wonderful lecture that we host every year. This annual event is possible because of the generous support of the Goldstick family, who identified a need and made a difference, giving students, scholars, and practitioners an opportunity for personal and professional growth. As of this academic year, the Goldstick family has supported over 34 fellowships, 11 research teams, and 4 scholars in the field of special education. This gift has had global impact, with past recipients holding scholarly appointments around the world, including the United States, Spain, and Chile. So thank you to Phil and the Goldstick family for the generous support you have shown the College of Education over the years. We are really grateful for your continuous dedication to supporting special education research here at Illinois. Before I ask Cheryl Leitschreiner to the podium to introduce this year's Goldstick speaker, I would also like to invite Dr. Matt Lambert. I do want to say new, but maybe not so new anymore. He is new, Department Head of Special Education, to say a few words. Matt has been with us for about a year now, and we're excited to have him here really providing support to our outstanding and top-ranked special education department. Thank you.
Well, thank you, Dean Musa. So on behalf of the Department of Special Education, I want to welcome everyone to this highly anticipated Goldstick Lecture. I'm excited for the lecture, which I expect to be a little bit different this year than in previous years, but will undoubtedly prove to be timely and thought-provoking in terms of how technology can reshape the field of special education and provide supports for individuals with extensive social and communication needs. The types of supports that were truthfully inconceivable only a few years ago. So the work that Dr. Rehg is doing to forge new paths to support individuals with disabilities is truly innovative, and we're fortunate here at the University of Illinois to count him as a colleague. He has so much to contribute to the field of education, and I look forward to exploring new projects with him over the coming years. I also want to take a moment to personally thank the Goldstick and the Zellinger family for their investment in research and innovation to support individuals with Rett syndrome. While this is only my second Goldstick lecture since joining the university as the department head of special education, I already feel a deep connection to the family because I also have a loved one with Rett syndrome. My niece Zoe was born in 2001 with Rett syndrome, and like Marissa, is getting older and facing a changing landscape of needs. And the continued support of the Goldstick and Zellinger families is helping the field to better understand and address the needs of individuals with Rett syndrome as they age. So on behalf of myself and my family, I want to thank the Goldstick and Zellinger families for their contributions over the years to support research on Rett syndrome through this lecture series and the many other initiatives that the families support. Their efforts and investments have benefited countless individuals and their families, so thank you so much.
I almost started reading Matt's stuff again. So, thank you, Dean Musa and Matt Lambert, for your statements. It is my sincere honor to have served as the Goldstick Scholar since January 2022. I want to thank Phil, Karen, and Gail, and the rest of the Goldstick family for your commitment and dedication promoting these innovative and evidence-based practices. Research and scholarship, and it changes and improves the lives of individuals with complex communication support needs, and it supports their families who are really looking for those answers. This is a true tribute to your forward thinking and your devotion to Marissa and others who have so much to contribute, and the families know that. And so when we have this research going on, we can make sure that we make that happen for a wider range of folks. In addition to hosting this wonderful event, the Goldstick family provides support to several doctoral students who have research and professional interests in improving the lives of individuals with communication needs similar to Marissa Zellinger. Marissa is the daughter of Karen and Alan and the granddaughter of Phil and the late Beverly Goldstick. I will be announcing this year's Goldstick Fellows and Zellinger Research Award recipients a little bit later, so we'll come back to that. Now for some logistics, I want to direct you to this very tiny QR code. And most of us have cell phones these days, and if you go ahead and take a photo of that, you can submit a question during the lecture. If you're a student, you can also log in your attendance, and I can make sure that whoever needs to have that information gets that information. For my students in 470, they get a ticket if they sign in and ask a question. So I want to make sure to remind them. In my class, they use their tickets to buy really fun things, including extra credit. So they're quite highly motivated to do that. But again, look for that QR code and feel free to submit a question. Then our fellows will actually be kind of screening through those, and when we have time for questions and answers, we'll have them share some of those questions with us as time allows. Now that was off script here, so I think I said most of that. At this time, it is my great pleasure to invite Marissa's mother, Karen Zellinger, to the microphone to share a few remarks of her own.
Good afternoon. Nice to see everybody. Wow, the 20th year for this annual lecture is awesome, amazing. We've heard from accomplished educators whose research looked at various areas of communication disorders, differing populations from age, abilities, and socioeconomic levels. We've heard so much, and today we are fortunate to learn about the intriguing area of AI, which is here to stay and is impacting all areas of our lives. Today's topic of leveraging AI to measure and models social behaviors is state-of-the-art, and I'm fascinated to hear how it's impacting the special needs community and how it will develop. I still have hope that our 37-year-old daughter, Marissa, with Rett syndrome, can benefit from this research and new technology. I'm so proud of my parents for taking the initiative with the College of Education to create this unique lecture for the college, for the university, and the local community each year. They handcrafted this gift with Marissa in mind in order for those in related fields of study to hear from the speakers who have been selected to present their findings on our campus and to share their work with us. Have them teach the graduate students and additionally offer scholarships to the outstanding students on campus who are conducting their research for the good of the educators, of all educators. The students in classrooms around the globe and ultimately are the ones benefiting, and that was and is the outcome desired by our family. We thank you for attending today and know that we will all learn a great deal. Thank you.
So thank you again to the Goldstick family for the privilege to bring another highly regarded scholar to the lecture series. This annual lecture has occurred for an amazing 2 decades due to this generosity. And again, they have shared in so many different ways in order to improve the lives of people with complex communication and social needs. Our 2024 Goldstick Lecturer, Dr. Jim Rehg, brings a unique expertise in electrical and computer engineering, as well as artificial intelligence. He traveled from the opposite side of campus, the Granger School of Engineering. Recently, he determined it was a 15-minute brisk walk, correct? When we were meeting over at the College of Ed. In addition to being the founding professor of the Computer Science and Industrial and Enterprise Systems Engineering program, that is a mouthful, Dr. Rehg has been a director of Healthcare Engineering Systems Center since 2022. He has an extensive history conducting research, teaching, and mentoring doctoral students and postdoctoral fellows and working within industry, Meta Reality Lab Research, Amazon Digital Equipment Corporation, is that correct? He has authored more than 50 journal articles, books, and book chapters. This list goes on and on. I was overwhelmed to see all that you've accomplished. It's wonderful. Dr. Rehg's current research and interests involve computer vision, machine learning, behavioral imaging, autism and developmental psychology, mobile health, and robotics. In a recent conversation we had, we also talked about his interest in collaborating with other disciplines like special education and speech and hearing science to apply existing computer technology and artificial intelligence to social and communication needs of individuals with a range of developmental disabilities. Please join me in welcoming the distinguished 2024 Goldstick Family Lecturer who has traveled, again, all the way from the other side of campus, Dr. Jim Rehg.
Hopefully that still works. There we go, perfect. Great, so thank you so much. So it's just a great privilege to be here today as a Goldstick Lecturer. This will be a bit of an unusual talk because I'm trained as a computer scientist. I'll be talking about how AI might impact developmental science and special education. When I began this journey about 15 years ago, one of our motivations was the study of autism. And I realize there are many here that are experts in autism, but for our purposes, the main property of autism is that it is behaviorally defined. And that means that if you have a child, you want to get a diagnosis, you bring them to an expert who looks at them, assesses them, and collects the evidence that's needed to make a diagnosis decision. Likewise, if you're getting treatment and you want to understand the efficacy of the treatment, again, you bring the child to the expert to be observed and to collect the evidence that's necessary. Now, we're always going to have experts interacting with individuals with special needs as part of their care. But the use of those experts to collect data is a laborious process, and it's not scalable. And so really the mission of my lab has been to change that, to provide automated ways to objectively measure social behavior. And there's lots of reasons to do this. There's lots of, societal arguments for the importance of studying autism. There's obviously the chance to help individuals and their caregivers as well. And if you think about, various ways AI could play a role, then there's, several things you can think about right away. So one is early detection, which has been a goal in the field for many years, still unrealized. And if you have the ability to analyze video, for example, and understand social behavior, that might enable in a more objective way to gather markers of risk for a condition like autism. Similarly, if you're looking at new treatment programs and you'd like to assess them, determine their efficacy, then you'd like some type of treatment measure that you could, again, administer in an objective way, in a cost-effective way. And we believe that video analysis could be a means to do that. So in this talk, I'm going to really be describing primarily advances in video analysis directed at understanding social behaviors. And that's kind of the program that we've been pursuing. So if you think about that, then there's actually a pretty straightforward way you can proceed. So the history of developmental science has given us many findings and observations about important constructs that are involved in social communication. You can see a list of them here on the slide, like social gaze, gestures, and so on. And then we also know a lot about how those constructs are combined to support more complex building blocks for communication, like joint attention, for example. So these are all constructs that are well defined. The challenge is to build models of these constructs that can be used to analyze video. And if we can do that, then that video, which is often collected routinely in the course of observation and assessment and so on, that video can then become a resource for measurement. And that's the challenge that AI could potentially impact. And here our focus is really like a laser on measurement. So there's lots of discussion around intervention, what treatment would mean for individuals with various special needs in the community and so forth. We are just trying to provide the high quality data, objective data, that could be used to support any treatment program that you might imagine implementing. So that's kind of our path that we're following. All right, so this is what I hope to accomplish with you today. I want to give you a kind of an overview of these different works that have been ongoing in the field around measuring a variety of dimensions of social behavior from video. And I want to just give you a sense of what's been done and what is currently possible, and then where the field might be going. Along the way, I hope to dispel some of the mystery around AI. It's really not as complicated as it seems as far as what's being done. And we can talk about where it might go in the future as well. Now, the starting point for this scenario that has been a focus of my lab for quite a while is illustrated in this schematic. So there's an individual interacting with a variety of people in an environment that has objects and so on in it as well. And the person that is doing the interaction that's the focus of our investigation, they're wearing a pair of glasses. And the glasses have a camera in them, typically right here in the bridge of the glasses. And the question we're asking is, how can we take the video collected in a setting like this and then analyze that video with a computer program, with an AI model, and then extract some information about what that person is experiencing and social communication that they may be participating in. So that's the kind of the setting. And this setting has a technical term, we call it egocentric perception, because the video is being captured from the perspective of the participant. You can see in that video their world from their perspective looking out into the scene. And we think that this egocentric perspective is really important for a variety of reasons that you can see here. But the main one that you're all familiar with is that it's very different to interact with someone as a first person, talking to them, versus watching people interacting, from a distance, let's say, in a movie or what have you. There's really no comparison almost between those experiences. We want to be able to capture that first person experience of an interaction with our cameras and then analyze that video to accomplish our goals. This also aligns really well with where the technology industry is going. So these augmented reality systems that are now coming, we'll see how well they're adopted by the marketplace, but they're giving us these sort of platforms, which are smart glasses people are going to hopefully wear, and then those cameras can capture similar kinds of data. So this technology could ultimately be deployed in many settings if augmented reality, becomes a reality. So we'll see what happens there. All right, so the first thing that we looked at in my lab is maybe one of the simplest problems, which is you have this video of someone doing something. In this case, they're cooking some scrambled eggs in a laboratory we have at Georgia Tech with a kitchen, fully functioning kitchen. And the question is, where are they looking? Okay, so now if they're wearing an eye tracker that does eye tracking, then, and there's many wearable eye trackers that exist, I'll show you an example in a bit, then you can just measure directly with the eye tracker where they're looking. But the question we asked was, could we predict where they're looking just from the image alone? So just looking at the pixels that you saw in that video, no other information, could we predict where they're looking? And the answer is yes. And so in this video, the little bullseye that's dancing around is the prediction of where the person is looking, and the green dot is the gold standard ground truth that comes from an eye tracker. So the eye tracker is there, it gives us the evidence of where they're looking, and our AI model is predicting that information. And so you might ask, how is this really possible, that you could just look at the pixels and guess where someone's looking? Well, these are tasks that involve hand-eye coordination. So the person is using their hands to cook, to manipulate the world. And because of that, if you can tell where their hands are in the video, if you can tell where the objects are, you've got information about where they're probably going to be looking. And we can use that then to build a model. And so this kind of gave us hope back in 2013 or so that we could really do this egocentric analysis and push it into many other domains. And so the first thing we looked at then in the social space is eye contact. And you can see a little schematic of that here. And the key position for us is that this is a basic social behavior, and it's one that we know is impacted in autism. So individuals with autism make less eye contact than typical kids and struggle in some ways to use it appropriately as a social cue. And we'd like to simply be able to measure it. So in a face-to-face communication setting, could you objectively, quantitatively measure eye contact using technology? That was the key goal that we set out to address back many years ago. And there's other ways you could think about this, eye trackers and so on, as I mentioned. These all have their role in research, but they're typically not used in clinical settings. They're very difficult to deploy in actual face-to-face, real-life situations. And we're really focused on technologies that would be deployable and usable in principle at scale, at a large scale. So here's the basic setup that informed this research. So there's a child. Typically, they sit in their parent's lap. They're sitting across the table from an examiner. The examiner is part of our team. They're wearing the glasses with the camera, and the camera, again, is right here in the bridge of the glasses. And so you can imagine in that setup, if the child looks at the examiner, looks into their eyes, like if you're looking into my eyes right now, you're looking right into the camera. You're literally looking at the camera. And if you're looking somewhere else in the room, off to the side, down, etc., then you're looking away from the camera. So this particular setup with the camera in this specific place, this lets us frame the problem of detecting eye contact as a pretty simple task. Just detect whether or not you're looking at the camera or you're not. It's what we call a binary classification problem, the simplest kind of problem that you can have. Okay, so we collected a large data set with our collaborators. You can see it here on the right. The little green windows are children that are labeled as making eye contact, and then all the other windows are children that are not making eye contact. Now, it's worth mentioning that the gold standard here is always human observation. So humans are the experts in social communication. When we want to know whether or not something is happening, we go to humans and ask them, tell us what's happening. Is this eye contact? Is it not? And then we have, raters that are trained to reliability using standard behavioral science methods, and those are the folks that provide the data that we're using in these algorithms. So collecting a large amount of data, as we did for more than, 8 years, and then training an AI model, that allows us to build an automatic system for doing detection. And this is what it looks like. So red means no eye contact, green means eye contact. This is a typically developing boy in our lab in Atlanta. We bring kids in and collect data from them in various ways. And then in a second, you'll see this boy here is a boy with autism at our collaborators' site at Weill Cornell Medical Center. He makes less eye contact than the other child, for example, but when he makes it, we're able to detect it with our algorithm. So there's an example right there of eye contact being detected. So this is kind of the program that we're following. So eye contact is a basic social construct. We have an AI model that can detect it in video, and we're pushing on that algorithm, and the goal of this process is ultimately going to be human-level accuracy. So we'd like to show that our AI model for detecting eye contact is as accurate as human experts would be in assessing the behavior. And this curve shows the ability to do that. So each of these little yellow dots is one of 10 raters that are all trained to reliability. So they're high quality data collectors for eye contact behavior. And then each of them is being compared to their peers. So the spread of these yellow dots is kind of the uncertainty that exists even among humans about a construct like eye contact. And so the green cross in this picture is our algorithm. Our algorithm is right in the middle of the distribution of uncertainty of the humans. In other words, if you took out one of the humans and replaced them with our AI model, the agreement among the raters wouldn't change. So the algorithm is as good as a human is from the perspective of rating whether or not there's eye contact in a video. And so this finding that we published a number of years ago at the time was the first kind of finding around using an AI model to measure a social behavior with an accuracy that's as high as humans. And we just want to keep doing this for all the constructs that are important. And once we do all of them, then we'll have the building blocks of social communication, and we'll have them in these AI models that we can then deploy and use in a variety of ways. Okay, so that's really the program. It's actually pretty straightforward, step by step. You just have to find the students, get the data, and then build the models. Okay. So then the next thing that we turned our attention to was another visual gaze-related construct, but more flexible and more broad than eye contact. Just where are people looking? Okay, so in this task, you've got a video clip, and there's two people that we're focusing in on. In the top row, we're looking at the woman, and we're asking the question in every frame, where is she looking? And the algorithm is supposed to put a little green circle that you see in the slide in the location where the algorithm thinks the gaze is being directed. And this includes cases where you can't tell where she's looking because she's looking out of frame or maybe looking at the camera itself. And so in those cases, we don't put any dot because we don't know where her gaze is directed. And so the second frame in that top example, she's looking at the camera, so there's no location of gaze that we're estimating because we just don't know exactly where she's looking. And then we can repeat this analysis for every person in the video. So you see in the bottom row, we're doing the same analysis for the man. And again, the question in every frame is, indicate where his gaze might be directed. And you can see different places where he's looking over the course of this video that the algorithm can identify. So this is another kind of basic video analysis problem that can benefit from these AI models. And I just want to take you through the solution now a little bit, step by step, and share some findings that we've had very recently that are actually not published yet that I think are very exciting around how AI can be used for these tasks. So this is the kind of more formal statement of the problem. So there's an image, there's a bounding box, that's the green rectangle, that identifies which face are we talking about, which person are we talking about, and then the output of this is going to be some kind of a heat map. You might be familiar with heat maps as they're used in eye tracking. They tell you a kind of a distribution over possible locations where the person might be looking. So the goal is to produce this heat map, this distribution, and then also label, of course, whether or not the gaze is in the frame or out of the frame. That's the algorithm's target. And then the data to do this comes from human annotators, once again. So we show this image to many people. We ask them, where is the boy looking? And they put little dots. You can see the green dots there where they think the gaze might be directed. And that set of dots becomes the data for determining where we think the attention is being directed. So this is a problem that's been around for, 5 or 6 years. There's been decent amount of work done on this problem by people in my community. And I just want to show you a little bit about how this is done, kind of as a way of hopefully dispelling some of the mystery. So really, this is an example of a deep learning architecture. You might have heard of deep learning and things like that before. But what this thing is doing is actually pretty straightforward. So there's two paths that you can see in the picture in blue and red. Think of these as just little blocks that analyze the image, okay? So the top path is asking the question, where in this image are things that people might look at? It's asking, what are the things that people might look at if they were in this image, part of this image, looking at the scene? And there's lots of work on what's called saliency, that you can get actually lots of models for where are the things that people might look at. They're more likely to look at people, less likely to look at a blank wall, for example. And that's the kind of analysis that top branch is doing. And the bottom branch is really zoomed in on the head or the face, and it's saying, well, based on how this face is configured, like how it's turned in the image and where the eyes might be directed, what are the parts of this salient image that are really more likely to be the gaze targets? And then that focuses the heat map on the specific regions that the child can see, and are likely to be targets for gaze. Okay, so that's really all this model is doing. The magic is really in some choices about the design and then the data actually that's being used to train it. Okay, so this was an early work. We did some work a year or two later. This is a model one of my students invented. We collected a data set as well, which was the first video data set for this task. But what's happened is that this modeling process has become more and more complicated. Okay, so this is an example of a recent model that was published a year or two ago, and I don't even want to begin to explain this to you. The point of this slide is this is very complicated. Okay, and this is complicated to computer scientists. Okay, not just anyone. And these models are incorporating all kinds of information about depth, how far away are things in the scene, the pose of the body, all these cues in an attempt to make the determination of the visual attention more accurate. Okay. And then this is actually a problem because coordinating all these modules in a big architecture and getting them to work together is really difficult. It's like coordinating, chairs or deans on campus, getting them to work together. It's very hard, and you don't want that to be the key to the success of your method, okay? Now, what's interesting is that in this field of AI, there's been a tremendous advance just in the last 3 or 4 years, and you might have heard of this term foundation model. And this has been a kind of a huge kind of way of moving the field forward in addressing complexity. And what this foundation model means is you've got this model that has been trained on a gigantic amount of data, billions of images, okay? And because it's been trained on so much data, it has a representation of the visual world that's quite flexible in general. So this model, which in this case is called Dino V2, that's just the name of it, this is a model that really understands a lot about the visual world in a kind of implicit way in these what are called weights in this deep model. And then once you have this representation, you can specialize it to a variety of tasks, and that specialization is actually pretty straightforward. So in the top image, you see a task called depth estimation, which means in the image, estimate how far away each part of that image is, where the brighter regions are closer to the camera and the darker regions are farther away. And you can see that this algorithm is doing a pretty good job of estimating, for example, that the table is closer to the camera than the couch, which in turn is closer than the wall behind the couch. The fact that this can be done, just from pixel values is kind of amazing, even to me. I would never have guessed this was possible, 15 years ago. Another task is semantic segmentation, which you see in the middle image. It means label everything in the image as to, what it is, and then pixels that are from the same kind of object, put them together. So the yellow pixels are all coming from the pillows, the blue pixels are coming from the couch, and so on. What's important about this is that this representation of the world isn't changing for these tasks. It's frozen, it's fixed. And then we're just training little models that use the representation to solve problems, okay? And that allows us to train big models that cost millions of dollars actually to train. And then once they're trained, we can use them for a variety of problems without doing any more, multi-million-dollar investments, basically. And so when we start thinking about this, the question we asked was, could we use the same approach for social behavior? Could we take these models that already exist and are freely available on the internet, actually, and could we, specialize them in some way that would allow us to predict gaze? And it's a non-trivial question because the people that built these models at big tech companies like OpenAI and Google and so on, they don't care about special needs. I mean, not systematically at least, and they don't really understand social behavior. The engineers that are doing this work don't really know these constructs. They're driven by a very different set of incentives and metrics to look at tasks like autonomous driving, for example, that could be someday worth a lot of money. So these models are emerging and they're very powerful, but no one really has investigated whether they're usable for the kinds of questions that we in this room might care about. And so my student Fiona Ryan looked into this and found to our surprise really, that these models are in fact pretty useful. So this is an architecture that she invented. The key property of this architecture is this Dino V2 block. This is this thing I was mentioning, this giant image analysis module that we just downloaded from the internet. And it cost millions of dollars to train, so we could never produce it ourselves in our labs. Totally impossible. But we don't have to do anything. We just take it and use it directly. And then what Fiona invented was all the stuff to the right of the slide, which is some additional logic that she came up with that uses this giant general purpose model to predict gaze, to predict where somebody in an image might be looking. And it turns out that this model is actually beating all the previous approaches in the field, these very specialized, very complicated architectures that were hand-trained and tuned in a variety of ways. Just taking this large, existing, powerful model and then specializing it for gaze produces the best performance. So let me just show you what that looks like. So this is an example of the output of the model on a variety of video clips. So that's a mistake right there. It's not perfect yet. Okay, so you get the idea. So then, and so it's pretty good. Okay, but it's not yet human level, not yet gold standard, human accuracy, but we're getting there. This is an example of out of sample generalization. These are just random YouTube video clips we downloaded and then applied the model to. So these are were not collected as part of the training or testing set. And you can see it's doing a pretty good job with these, although it still makes some mistakes. All right, so that's the the interesting finding that I wanted to share today, and I can tell you a bit about what I think is important about it, but I just want to make the not obvious, but make a specific point, which is that you need to actually think about how to use these models. If you just take existing architectures and try to plug this Dino V2 thing in there, that actually doesn't work very well. So there's some specific insights that Fiona had that ultimately produced the results that I'm showing you. But I think there are some potentially powerful implications, for this finding, because what this tells us essentially is that these existing, AI models that you've been reading about that are out there already on the internet, you can download them if you want and play around with them, they may already contain extremely rich generalizable representations of human social behavior, even though the people that built those models had no interest in that and didn't intend for that to be the case. Because of the types of data that they were trained on, because of the richness and the complexity of that data, these models are maybe much more powerful than we thought. If that's true, then we can begin to think about a different approach to modeling social behavior, where our focus is not on collecting massive data sets of children that we can then use to train AI models. We can focus on collecting smaller data sets just to specialize these models that exist already. And then we can ask a question that we haven't even really begun to ask, which is, how will we know if these models are suitable for a particular purpose or not? And we never asked that in the past because the idea of collecting that much data from a representative, diverse cohort of children all around the world doing a variety of social tasks was just too daunting. If the goal was to train the model, we just couldn't afford to do it. But I think you can afford to do it when the goal is assessment. And so that's the thing we're embarking on right now. We're starting a new project to essentially build a kind of comprehensive data set of nonverbal social communication, ideally sourced from children all over the world in a wide range of contexts that will target a wide range of developmental tasks that are well known from the literature. And the purpose of this data set is simply to benchmark these AI models, to assess how good are they in solving these kinds of tasks: gaze estimation, gesture recognition, facial expression analysis. You can figure out the list, right? And then the idea is to make this into a kind of a service, for the developmental community, that you can go somewhere and check, how are we doing? What's the current performance of AI models? You can ask questions about tasks you care about, and then find out whether or not the technology is good enough. And we're pretty confident these models are going to keep coming. Every year there's a new one. Every year that new model is better than the models that came before it. So I feel like at some point in time, it's going to be good enough for human level accuracy. At that point, it's going to be a tool for the community as a whole to use. So we're just beginning to kind of start this project and collecting some collaborators that will hopefully allow us to pull these different data sets together. And I'm very excited about that. All right. So I've been talking to you a lot about these kind of very basic communicative constructs like, eye contact, visual gaze, estimation. I want to kind of take things up a level, so to speak, and talk a little bit about more complex constructs and just give you kind of a sense of what's happening there. And then I'll show you a few other things that are interesting that are related to this, and then we'll be able to conclude. So one of the most basic constructs that we would be interested in is what's called joint attention. Again, probably something many people here are familiar with, but this represents kind of an evolution from eye contact, which is like dyadic gaze. I'm looking at one social partner, looking at in their eyes, to an interaction that's more complex, that involves shifting attention around the environment, looking at objects in the environment, looking back at my social partner, and that coordinated change of attention, which can be gaze as well as gesture and so on, that becomes a way to communicate interest. I'm interested in this object. What do you think about this cool toy? And so we know that children exhibit this joint attention at an early age. We know that it's really important as a building block for social communication. And this has been established by a variety of research, and I'm just showing you some examples of different types of joint attention here that are documented in the literature. And this is something that has been shown to be important for understanding autism as well. So this is an old, relatively old finding now from the early 2000s. This plot on the left, each of the trajectories in that plot is one individual with autism. What's being plotted is their language age in months, so their facility for using language, against their chronological age. And so the orange bar is the kind of typical development baseline. It's the normed baseline in that chart. And then you can see that there's quite a heterogeneous distribution of trajectories. So some of the kids with autism are acquiring language essentially as rapidly as the typical norm, and other individuals are making very little language gain. These are the horizontal lines in that chart. They're making very little language gain as they get older, which is really a problem that you'd like to address. And so the question that was asked, at the time this work was being done is, what could you measure at intake? What could you assess in a young child that would help you understand which of those trajectories they would likely be on? Whether they be a child that was going to make significant language gains, or whether they might be in the group that's going to be, making much less gains over time. And people investigated lots of different measures at that time to try to figure out what could give us some idea about the outcome. And the thing that ended up being predictive was joint attention. So if you take these children at intake and then you assess their joint attention skill when they're like 18 months, for example, that skill that they exhibit at that young age is actually predictive of their language gains, 4 years later, which is a huge period of time, developmentally speaking. So this joint attention construct was shown to be really powerful as a kind of an early piece of evidence for facility in acquiring language. And that in turn is the reason why it's often been a target of early intervention, and it's something we often measure in children as well. And this is just the evidence to support what I just stated. So this is stratifying this sample into two groups. The top curve that is making better language gains have a high rate of what's called response to joint attention, and then the lower bar, the lower trajectory in the dashed lines are children that had much less responsivity to joint attention at intake, and these are a way of stratifying this sample into two groups, one that is gaining quite a bit of language, one that is not. So this finding really establishes the importance of joint attention. But one property of this is that the way that joint attention is being measured here is relatively crude. So there's a coding scheme that was invented by Peter Mundy that's part of this overall protocol we're following and collecting data. And the labels for this are relatively coarse. So in a grant that we had a number of years ago, we asked the question, if we had more fine-grained measures of joint attention coming from more complex automated analyses, could we make better predictions? And so there's some work that's ongoing in my lab to try to look at that hypothesis. We don't have the core findings yet, but I can show you some preliminary results. So this is the result of applying our visual attention model in the same setting that joint attention is being assessed. You can again see the heat map here that the algorithm is producing. You can see how it moves around as the child is looking in different locations. And then on the right is some performance of a classifier that we train that's trying to predict predict the joint attention codes, essentially, that were being produced from this video. And you can see the accuracy around 0.7, so it's not anywhere close to being as accurate as humans are, but it's a starting point. So we're building on this result in new work that we're doing, and the goal is ultimately to be able to produce a more, kind of hopefully richer and more accurate description of these joint attention behaviors. All right, so that is kind of, in a nutshell, kind of this paradigm for analyzing video of children and then building up successively different layers of assessment of their social communication skill. And I want to transition a little bit and talk about some other related work in assessing conversational interactions that we're doing with adults. And in general, we're trying to do this in both populations, that adults have these complex social skills. It's the most complex sort of setting in many ways you can analyze. And then it's easier in many ways to outfit adults with various sensors, so we can try to explore the utility of sensors in that population. And then we often get findings from working with adults. We bring those findings back to the children and use them in other contexts. We're kind of working on both ends, so to speak, of the developmental scale in the work that we're doing. So this is a recent project we did with collaborators at Meta, and the goal of this project was to look at a more complex analysis of a multi-person social interaction. So now it's not just a child and a caregiver playing at a tabletop with toys, it's actually a group of people that are interacting in more complicated ways, and they're speaking, they're using language, as well as they're gesturing and they're looking. And the question is, could we analyze that type of data and figure out who's talking to who? Okay, so this is a group conversational behavior setting. You can find many examples of these in real life settings. You know, you're at a dinner table. Many people are talking in parallel to each other. They're talking over each other. They're talking to someone, and they shift their attention to someone else. So it's a very complex, dynamic setting with complex, conversational behaviors. And the question is, if you had, again, wearable cameras, if those cameras also had microphone arrays, so you could actually understand the audio, not just the loudness of the audio, but the directionality of where the audio is coming to that person wearing the sensor, then you have this ability to kind of tease apart, this complex pattern of interactions and try to identify, oh, this person is talking to this person over here right now. Oh, and now they're talking to someone over here, and this person is talking over there. Now, there's lots of interesting reasons why you might want to do this. For older adults, this could ultimately be the basis for something you might think of like a smart hearing aid. So folks with hearing impairments, you'd like to help them to understand, to hear better by, for example, amplifying the sound. And right now, a lot of that technology is based on just across the board amplification, maybe amplify the frequencies in which speech occurs. But if you're in a multi-talker environment where there's many people speaking, then all the sound gets amplified. It actually can make the problem worse, for the person that's wearing the hearing aid. So here, you could imagine if this were ultimately successful, you could figure out for this person, oh, they're actually talking to this person over here. And then you could selectively amplify just the sound coming from that direction and amplify those sounds to that person. And then actually you could kill all the other sound that's impinging on them from other directions. So you could make this, amplification much more selective if we were to succeed in doing this. So this is the setup. We have people who are talking to the person wearing the camera. We call that the egocentric, behavior. And then they're also observing other people in their environment talking to each other. So that's what we call exocentric, meaning you're looking out into the scene and asking a question about other people. And we'd like to model all these patterns of interaction as they're happening. So we think about the total pattern of connectivity between people, any of those, this is a little bit of a graph essentially, which you can see on the right. And each of those little links or arrows or paths is a connection from one person to another. We'd like to figure out, who's talking to who's listening to who. And then we can decompose that into people that are talking to or to the person that's wearing the camera and people the camera wearer might be listening to, and then the other set of combinations, the link between people that I'm observing as I look out into the scene. Okay, so we built a model. One of my students, Wen Jia, did this work as an intern at Meta, and this model takes these video frames as input and produces as output what we're calling the conversational graph. So the conversational graph describes who's speaking and who's listening to who over the course of this multi-person, multi-party interaction. Okay. Now, one of the biggest challenges actually in doing this work is understanding what's happening. As a human observer watching this, it's impossible to tell essentially like who's listening to who, if you just go on kind of the surface perception, because, with our visual perception, you look at the eyes, you can tell where somebody's looking. But for hearing, you really can't tell, right? There's no sort of overt sign of what I'm listening to. And so the way we collected the data for this study is we had a cohort of people, you'll see an example in a second, and they were given instructions in the beginning of data collection who to talk to and who to listen to. Okay, so there's multiple people in this room, but each person is only going to talk to and listen to a small subset of the total people, and that's known in advance. So then we know, from a labeling point of view, we know who's talking to who's listening to who. Our AI model doesn't know this, of course, and then has to figure it out, by using this data and analyzing it. All right, so there's another deep learning architecture involved. This one is analyzing video and audio together. So the novel thing about this compared to the previous one is now there's audio as an additional channel of information, and they're being combined in a standard way to fuse the vision and the audition together and decide essentially, who's listening and who's looking at who. This is some performance in terms of accuracy. I'll skip over this. I don't think it's super important. you know, this is the kind of thing we have to do in my field. You always have to do a tremendous amount of quantitative analysis to get your papers published. And so you're always seeing these tables. And then the way it works is, you know, the bold line is my performance of my method. And then all the other things that are not bold have to be worse than me. Okay, and then I say, oh, see, I'm beating everybody in this table. And then you publish the table in one meeting, and then 5 months later there's another meeting, and somebody else has a table, and now you're the worst, and they're the best. And the field goes on in this kind of, you know, table-based arms race that all my students are locked into, whether they like it or not, basically. So anyway, at this moment in time, which was last year, this year CVPR in the summer, at that moment in time, we were ahead of everybody else. All right, so I just want to give you a little taste of how this is working. It is actually quite challenging to see what's happening here because it's just, these conversational interactions are so complicated. But I'll play the video first. You'll get a chance to hear a little bit of the audio, and you'll see the people kind of how they're interacting. And then I'll play it again without the audio so you can listen to me, and I'll explain kind of how the model is doing its work. So that's a little clip of the conversation we're working with. The participants are wearing some special glasses that were built at Meta that have the microphone array and the camera built into them. And then you'll see now just what the algorithm is doing. So it integrates information over some period of time, and then it produces this graph. Each of these arrows is showing, oh, listening to, speaking to, and then on the right is the ground truth, what actually was going on. On the left is our prediction. If the graphs look the same, then we're doing a good job. You can see there's some mistakes going on in these graphs. But to be honest with you, even for me, it's really hard to know if this is working or not. So I kind of have to rely on my students that have all the quantitative data. You know, it's just so complicated as a human to follow multi-party conversation, you know. But this is like a starting point. This was the first piece of work, actually, that was ever done to kind of tackle this problem the way we're framing it. And I think we can begin to build on this and then think about more complex and in some cases more developmentally relevant ways to measure patterns of interaction. You can think about a classroom setting and things like that. This could be very interesting. All right, I want to end by just showing you a few things that are much less far along, kind of works in progress, if you will, and just building on the theme of understanding social interactions more broadly. We've been involved in some data collection activities, looking again at this multi-party conversation and looking at them in very specific tasks, some very specific settings where we can ask deeper questions about how are people using communication? What is their purpose actually in communicating? What are they trying to accomplish? So that's going beyond just the what's happening to beginning to ask questions about why. You know, why is this person talking to the other person? What's their purpose in doing so? And so we collected a data set a number of years ago that's part of a large computer vision data set called Ego4D. And this has been a very impactful piece of work. It's been cited hundreds of times already, and it's been used by a lot of different disciplines. And part of this data is very interesting data of social interactions, people interacting socially in their homes, playing a variety of games. And most of these have been games that are sometimes called social deduction games, like One Night Werewolf and Mafia. These are games, you might have played them yourself, where people have roles, and then you're trying to mislead other people about what your role is. They're trying to figure out what your role is, and it's all about conversation and deception and so on to try to become the winner of these games. And so we collected a pretty large data set of people playing these games and used really a rich variety of sensors in the process that give us this egocentric point of view as well as a point of view in the scene. And I just want to show you one example from one of these games. These are some people playing the werewolf game, and there's an individual in this example here on the left-hand guy. He's trying to persuade the others about his role. Okay, so take a look. So this guy was trying to mislead the others. He was trying to bluff his role. He didn't do it in a great job. He wasn't persuasive at all. And then his friends immediately called him on it and said, no, you're lying to us. It's not the case. Okay. So these games are very interesting because they involve, persuasion behaviors. You're trying to use your language and use your, your words and your gesture and so forth, facial expressions. You're trying to persuade other people about something being true. Okay, so we're very interested in this question of persuasion. It's a basic kind of aspect of social communication. We'd like to know how people do it. What strategies do they use? What determines whether somebody is successful in persuading others or not? And so we collected this data set as just the beginning of this process, and we annotated this data set by identifying some strategies, if you will, that you can use for persuasion. So for example, you might, as part of your persuasion strategy, you might interrogate somebody else. You might say, well, what are you? What's your role? And you're doing that as a way maybe to put them on the spot, get some information, maybe take suspicion away from yourself, for example. Or you might call on others to take an action or to believe something to be true. And so we identified these strategies, and then we labeled this data set at the utterance level, utterance by utterance, whether or not a strategy was employed. And you can see some examples of that labeling here. And so this became now a data set that's available to the community to use to tackle this problem of persuasion from the perspective of face-to-face social interaction with audio and video context. This is a very complex task for persuasion. There's lots of other data sets that were collected in simpler settings that were not multimodal, but this is the first one to bring these modalities into play. And then one of the things we can do with this data set is we can try to predict how people are going to vote at the end of the game. So at the end of these games, typically you've got to state what you think is true about the world. You say, I think this guy's the werewolf based on everything that's happened so far. And then the game forces you to take a vote. Say, I think the werewolf is this guy. Okay, so that voting behavior is an objective expression of your belief about the world. So if you're familiar with theory of mind, then these are really theory of mind games, where essentially you're trying to influence somebody else's, belief about the state of the world, and then when you vote at the end, you get a record, actually, what everybody believes to be true about the situation. And so one of the tasks we can tackle with this data set is trying to understand ultimately how this theory of mind works as a computational process, and then we can begin to make predictions. We think this person is going to vote for the werewolf being over here because of the analysis we've done of the video and the audio. Okay, so we tried a little experiment to do that last year. This is my student Bo and Lai's work. This is a paper we had at a conference last summer. And you can see the accuracy again, without getting into all the technical details. The F1 and AUC are both numbers that should be big. If they're 100%, you're doing a great job. You can see that they're very low actually here. So we're not doing a great job. So this is a very complicated, construct to try to predict what somebody believes to be true about the world. Very hard to predict that. And so we're not there yet. But on the other hand, we can look at it for the first time with these modalities. So we're very excited about continuing to work on this, and then over time, build up better models and tools for understanding these more complex behaviors. All right, so I've kind of taken you through this landscape of first looking at basic things like visual attention, where you're looking, then talking about how could this be used as the basis for understanding joint attention, and then moving to adults and asking more complex questions around naturalistic, multi-party conversational settings. And I'd like to end by talking about something that's very new that we haven't really started yet, but I'm really keen to start here at UIUC, which is kind of branching out and supporting things other than social communication, and looking in particular at folks that might have an intellectual disability and might need supports to be able to accomplish tasks because of that ID that they have. And so we're starting to ask these questions, and this is very preliminary work, so I'm not going to show you any findings. Well, I'll show you a finding, but it's not directly relevant to these questions. But these are the kind of things we're wondering about, basically. So we're looking into the future, and we're imagining that these AR glasses might be available, very capable and powerful, and maybe people will start to wear them. And if that was the case, could we give the AR glasses to an individual, to an adult, let's say, that needs some kind of cognitive supports to get through their daily life? And that glasses could have inside them an agent that could inform them about things they need to do and help them to be more effective in navigating through their world. Okay, so this is just an idea, and for this to be a reality, we would need to not just develop the technology, which is already challenging in its own right, but work with folks like you all in this audience to understand how can it actually best be used, how could that information best be communicated in a way that would actually make a difference, could actually improve outcomes. So this is a big challenge. By no means do we understand how to do it yet. But I'm excited about the advances in these platforms. So these are two recent announcements, one from Meta, one from Snap. These are new AR glasses. These may look unfashionable to you, but these are the most attractive glasses of this kind ever created so far, okay? I could imagine my mom wearing the top pair of glasses. I could not say that about any previous glasses coming out of these companies in the past, okay? So maybe someday these glasses will be wearable enough and powerful enough that we can use them for these kinds of tasks. Another thing that's very exciting actually are what are called hearables. These are essentially earbuds on steroids that have lots of computing power inside them. They can pass audio through, but they can also overlay computer-generated audio. So you can think about someone in your ear talking to you in some appropriate way that's hopefully conditioned on the context as well of what's happening around you. These are other platforms that are under development. Many companies are working on these, including Apple, for example, so you know that there's going to be big investments and resources. So can we utilize these? So I wanted to show you one quick idea of how you might do something useful in this setting. Okay, so this is a different problem, a little bit different problem than what I mentioned. It's a problem of giving somebody instructions when they want to know how to do something. Okay, so suppose I'm wearing a pair of glasses and I'm doing some washing, and for some reason, don't ask me why, I've got this question: how do I wash the trousers? Okay, and that's my question. Now, you've all used ChatGPT. You can fire that up. You can say, hey, how do I wash a pair of trousers? And it gives you an answer. Quite a good answer, actually, for these kind of things. It's actually quite good at this. But you've got to read them, okay? And you've got to translate them into your setting, because I'm washing the trousers right now, with some stuff around me, and that's my context. And ChatGPT has no idea what you're doing with your trousers, okay? Now, suppose I can capture an image. The image from these egocentric glasses from my point of view. Now, the image shows the context. It shows the trousers I'm working with. It shows my hands, various things. And it turns out, with the new ChatGPT, you can give it the image and the question, how do I wash the trousers? And you'll get a better written description as text output, because it uses that image as part of its analysis, which is quite amazing, by the way. This happens, off the shelf in these models. But you still have to read. So what if you just wanted a picture? What if you just wanted to see what I should do? So that's the work that we presented at a meeting just a few months ago, computer vision meeting. And this is an image that was synthesized by one of these generative AI models. So the image on the bottom right is not a real image. We created it from an AI model. And that image is showing you in a picture what to do. Hold the brush, put the trousers here, do something to make them, to wash them. So this is an example of taking a question and then using the view of the person from their glasses and then making a picture. Here is what you should do. Okay, so I'm not proposing that this is usable, okay, in any specific way. Okay, it's just a piece of technology. Just getting this image to not look bad was hard for my student. Okay, so we're very proud. This image does not look bad, okay? But that doesn't mean it's suitable for any purpose yet. Okay, so think of this just as an idea of something that might be done in the future if we keep working. Okay, so I'll wrap things up. This is the architecture that does this. It's very complicated. I'll skip all that. And then this is just showing you some results. So these are some images. These are the associated questions. Each of these second row of images, the second columns are the output of our algorithm. And then these are real images captured from the glasses a little bit later in the process that are relevant to the query. So you can kind of see a visual comparison side by side. Again, my main point is the images don't look bad. Okay, that's my main point. All right. I'll wrap things up. I just want to thank our various sponsors over the years for all this work that we've been doing. I want to thank all of our collaborators at Georgia Tech, at Weill Cornell, and of course now in the future looking forward to collaborators at UIUC. That's hopefully how the slide will change going forward, as we'll add more names to this list. And just to make the conclusion, so the thing I would really emphasize is that we have the means, okay, to collect rich data of social behavior in real world settings, using platforms, cameras, glasses that are feasible. They're affordable, they're deployable. And we also have the means to take existing AI models and repurpose them to analyze this video, to measure in a quantitative way things that we know are important for social communication. So we have the means to do both of those things. Okay, right now the means exists. And the challenge is to do this in a way that is actually impactful, that actually moves the needle on behavioral science research, that moves the needle on caring for special needs individuals. And that is where the real work lies, is working together to use these technologies that in many cases we didn't create, but we use them to really do something positive and powerful. So I look forward to working with you all on that going forward. Thank you.
Students are busily coming up with a couple of questions. And I wasn't sure if for captioning I had to be close to a microphone or not, so I do. Okay. We'll see if we have a question, and then I'll get out of the way. Can she say it loud, or should she come to the microphone?
Is this mic here?
I think here.
Okay, I see.
Will this one work? Yeah. Okay. And I can be that person, so.
Thank you so much. This was great. We do have a couple of questions. Some of them are extended questions, so I'll try to summarize it, but if you need help with getting through it all, I can help you with that. So one person had a question about kind of the practicality of factors that might influence the motivation of eye contact. So they were really trying to understand the glasses that people are wearing. Are they more like sunglasses, or are
Yeah.
they more like eyeglasses? And then also what your team did early to kind of choose which like
Yeah.
wearable system you were using.
Yeah, that's a great question. I didn't get to it in my talk, but I can answer it now. So one of the kind of big questions in all this work, right, is this question of reactivity. Like, if I bring a sensor into the interaction with a child, do I change the interaction in some way? Do I influence the child's behavior in some way? So we were worried about that early on, and we did a study with Wendy Stone's group at UW, where we had 3 different glasses conditions. There was no glasses. These were moms interacting with their children. There were no glasses. There was some fashion sunglasses, and then there were our little eye contact glasses that had the camera. And we had a protocol we followed where we could tell where the child was looking, and we had the video of those glasses, and we could figure out, what was the pattern of behavior of the child. And so we were able to figure out in that context that there really wasn't any influence. So the glasses condition, regular glasses, sunglasses, our glasses, didn't change the child's looking behavior. So that was like one study we did to try to get at this issue of whether or not the sensor we introduce is going to affect behavior. But it's a really important question, and we did this one study, but then the technology changes, right? New glasses come on the market, new technology emerges. We have to essentially constantly be assessing this. And there's obviously this, real concern around stigmatization. If I'm wearing something that looks weird, it could stigmatize me as someone who needs supports, and that might, for example, not cause me not to adopt that technology, even though it might help me in some way. So looking into that carefully and figuring it out is an important part of the overall, research agenda. And really, I'm hoping that the folks that are making these glasses, they will do our job for us. They understand very well that the glasses look weird, nobody's going to buy them. So they're incentivized to produce glasses that look like mine, eventually maybe, but have all this functionality baked into them. And I'm just hoping, that they get that done fast enough before I have to retire, for example. But it's a great question. Yes.
Here.
Just the visual thing with the young kids, is that implying that there's sort of a lip reading function going on with the children in terms of learning language? That if they're not able to focus on the face, that they're not going to be able to learn language as fast because there's a kind of a lip reading thing going on with language?
Yeah, so I'm not a developmentalist, so I'm probably not going to take a stand on exactly what's the causal mechanism at work. I think we're really just looking at objectively measuring the behavior. And then a lot of times the gaze that we're talking about is really social gaze. So the child might actually be looking at a toy and then looking back at their social partner, looking back in such a short period of time, they're probably not able to lip read. It's more like they're checking in, hey, what do you think about this? So there's this social component to gaze that's really what we're getting at with these methods. But as far as I know, there's lots of research questions around the underlying processes, how social communication is acquired, how it might be disrupted, in different conditions. I'm not going to be able to speak to those causal mechanisms, directly. So it's a little bit of, unfortunately, kind of dodging your question because I'm not,
It's just very interesting.
Yeah.
I ran into an adult, I'm talking about children, but I ran
Yeah.
into an adult the other day who had a big hearing problem. He has one of those implants.
Yep. Yep.
And he was telling me that he actually is very good at lip reading.
Mm-hmm.
He's very good
Yeah.
at lip reading, and that helps him even when he's not wearing that thing. But I just wondered if that is, I don't know if anybody else has, if that's a part of this problem, is that if you're not able to
Right.
focus on the face of your partner, your parent, your teacher, that your language development is going to be impaired.
Mm-hmm.
And maybe that's
Yeah.
a spin-off of that. So there's maybe ways of getting better attention.
Right. And there actually is a lot of work, it turns out, in my community on lip reading. It's been studied for quite a long time from video, and there are models for it that are pretty good, actually. Again, lately, performance is getting better and better. So to the extent that that's an important modality, we can actually potentially do that computationally, again, from the same wearable vantage point. So it's a good point. It's a good observation. Yeah. There's a question right back in the back there.
Thank you for that really fantastic talk. You were saying that humans are the kind of the gold standard for this work, but is it conceivable that this kind of AI could become more powerful than humans, even expert humans?
Yeah, it's a really fascinating question. You know, so for that to be the case, we would have to have a much better understanding, I would say, of what is the underlying data that would be used to answer that question. You know, so I think that's the difference. Is with humans, we don't. I mean, we do have ways of doing assessment, obviously, but we're not assessing humans in the same way that we would assess an AI, because the AI has to work across all settings. You know, it has to work for all kids, you know, ideally all languages, all parts of the world, all social contexts that include cultural influence. You know, so there's this high bar in a way for AI, which is appropriate, you know, because it should be a universal tool, not just limited to one region or one group of people. And so that, I think, my sense is that's a research question for the field. Like, even to understand how to assess that exactly is not really clear. But you know, you're hitting on something interesting, because we've seen other areas where AI has, in some sense, you know, been able to achieve what you might think of as superhuman findings. Although often I think what really that means is that there are humans that are actually super. Okay, so one example, an early example was there's a famous data set called ImageNet. One of the things that data set includes are different breeds of dogs. Okay, now if you ask an average person, 2 pictures, you know, what are the 2 breeds? Many people have no idea. They're just dogs. You know, I have no idea of Samoyed, what is this thing, right? But the AI model, because it's super specialized and it was told, you know, these are the properties of different dogs, it can make really expert predictions about the dog breeds. It can do it better than the average human, okay? But probably not better than a dog breeder, you know? So specialized humans have the specialized capability. They may be the ultimate pinnacle of expertise. It's not clear to me if AI can actually exceed that. What we often see in these findings is that humans themselves are really variable, and some people are not really paying attention. They don't find the task to be very interesting. They're answering some random ways, and they drive down the average, you know. And then the AI comes in and says, whoa, look at this, I'm better than these guys. Well, yeah, maybe some of them you're better, you know, maybe you caught them on a bad day, and then other ones not so clear. So I think we have to take these kind of findings about AI with a grain of salt, you know. But these models are very specialized, and they have biases also, but they're very consistent, even in their biases. So, you know, that's the power of these models, is kind of this deep specialization and consistency. And the challenge is to use them in ways that overcome their biases and other factors that, you know, we're working on. So it's a very provocative question. Who knows?
One more? We have time for one more. So, would you be the one?
Oh, sorry. Yes, you know, like, it's mind-blowing what you showed us, really, and the potential and where it's heading. And of course, it's changing by the day, the tools, the whatever. But I just want to ask you a specific question as educators. So we can talk about corpuses that are out there, you know, that have everything. But what's our role in shaping and designing corpuses for specific purposes? Maybe it's for kids with disability. And then how do we get to understand the kinds of prompts and questions we ask in relation to that corpus? Is there a lot of work being done about that relationship, that, you know, for specific purposes in, you know, and specific people and specific tasks? Is there?
Yeah, I mean, I think the answer to your question is, so okay, you asked 2 questions. You said, what is our role? And then you said, what's being done? So the answer to the first question is, I mean, it's everything. Because if there's no role, if you guys don't play a role, then if things happen, they're probably the wrong things, you know? And then what's happening now, the answer is probably almost nothing. I mean, I'll give you an example of what is happening. So autonomous driving until recently was a really powerful driving application for my field. And there was a huge amount of money, hundreds of millions of dollars being poured in to creating autonomous driving systems, which included computer vision analysis of the kind that I'm showing you as a key part of that technology. So this was an investment being made for the purpose of creating these autonomous cars that would ultimately make a huge amount of money to the winner, okay? And so in that case, the engineers could do the assessment, and they did a pretty good job. So they would say, what are the properties of autonomous driving where perception plays a role? Well, pedestrian interactions, understanding intersections, understanding different kinds of roads, dirt roads, gravel roads. And so people built these massive data sets of people and road types and intersection topologies, and they really quantified it, you know, pretty well. And it's still an ongoing area of research to kind of, you know, quantify autonomous driving systems performance. But that's a work that my community can do because it doesn't require specialized expertise. It just requires you to drive, which many people can do. Okay, so it's easy, right? But what you're asking about as an educator is, you know, understanding what makes some children learn in a setting and others not, and what can be done to improve the outcomes of learning based on the contextual factors that are there in the classroom or in the instruction. I mean, this is a very specialized thing. No one in my community has the expertise, you know, to look at that. And so far, most people are not looking at it. But if they start looking at it without talking to you guys, they're just going to do random stuff. Okay, so I really hope that doesn't happen. I think we should really find a way to work together, and I would rely on you guys to ask the right questions. You know, what are the things that matter? What are the settings in which you should do assessment? And then we could figure out on our side, you know, how could AI be useful in those settings, and what would we do to measure whether or not it's good or bad? But without that, I don't think we can go forward.
I just have to find the right page. Thank you, Jim. I found my spot. So interesting, and I have a million questions, but we, of course, didn't have time for all of those. So hopefully I can ask you tonight or tomorrow some of those questions. You've given us many things to think about, different ideas. I think we're just scraping that surface of what we could do, you know, for assessment and prediction and early intervention. At what point, if people, I even had the question of your data collectors are collecting from a particular perspective, and are they neurodivergent perspectives? So maybe there are people that actually perceive and would collect that data in a slightly different way. Anyway, we can talk more about that, but very, very interesting. It actually promoted way more questions for me, but that's really exciting, and especially exciting because you want to collaborate with folks like us. So I think that's going to be wonderful. We did our questions. So right now, I want to get to our announcements of our wonderful students who, thank you for helping me today. But I do want to acknowledge my predecessors as Goldstick Scholars. So we had Jim Halley, who's out there somewhere. He said he was going to be on the live stream, Mickey Ostrowski and Hedda Medan, who have really been instrumental in making this series be successful. And so I've just been pleased to be able to learn from them and benefited by their mentorships in this whole process as well. Behind the scenes, we have so many people that made this event actually happen. So Allie Stevenson, Heather Zorn, Stacy Wombles, Gina Manola, Ashley Lawrence. We had all our folks that did our captioning, that kind of thing, the live streaming. So thank you all. It wouldn't have happened without all those people behind the scenes. If we could give them. So 20 years ago was a long time to have started this whole process. And recently I actually sent Karen just some more recent information about all the different scholars. So I think I think there's been 50 fellowships given out. So that's a lot of support for doctoral students. And so what a way to honor Marissa and the whole Goldstick family, right? I mean, I just think that that's wonderful that all of these young people are out there doing research to benefit other people. We want to also always remember Beverly Goldstick as her role in the family and as, you know, a motivator for these scholarships and that kind of thing. Beverly was not only a loving and caring wife, mother, and grandmother, she was also been a very good friend of the University of Illinois in different entities within the university. And she has been a friend to lots of people and continues to be missed by people. So our Goldstick Fellows, we have 4 this year. One is not able to be here, but we were able to select 4 doctoral students, 1 from the Department of Special Education, 3 from Speech and Hearing Science. We have this collaboration with our folks in another college, and that has been really wonderful. So as I call out your name, if you could stand up and just kind of wave at folks. Our Goldstick Fellows are Megan Best, who is not here, but she's at a conference and that kind of thing, but she has wanted me to say thank you to all of you for her fellowship. Alexandria Barkheimer. Kayun Karen. Wang. Daniela Fanta Alakan, thank you. They have been so helpful today, and it has been just a joy to be able to provide you with some support. And again, thank you to the Goldsticks for that opportunity for you. We've also had, again, we have a committee of folks that go through the applications for those fellowships. And so I want to recognize Michelle Schutz from the Department of Special Education, Marie Moore, Chanel from Speech and Hearing Science, and Laura Maddie from Speech and Hearing Science for assisting in helping sort through so many wonderful doctoral applicants and to be able to make those selections. So let's just give them a round of applause. We also had the opportunity to select the Marissa Zellinger Research Award, and that is an award given to a faculty member and a doctoral student to continue some research that they're doing. So that was Dr. Michelle Schutz and Megan Best. So let's give them a round of applause. This award is designed to enhance the research mission of the Department of Special Education and to contribute to scholarly literature on topics relevant to Rett syndrome and others who experience complex communication needs. The research is an extension of the research funded last year and seeks out the perspectives and experiences of youth who use augmentative and alternative communication and their families within the transition planning process. So these are older students who are leaving the educational system onto adulthood, and includes them as co-researchers, which is the new component of this research, that they're actually contributing to research questions and things like that. And so they've got the folks using AAC as part of their team. Their contributions are critical for informing practices that are grounded in the lived experiences of the disabled community. And I think it's long been missing out of a lot of our research. The qualitative findings will have important implications to inform the field and educators who support youth who use AAC in directing transition planning and achieving post-school goals. It is also exciting to have AAC users serve as those co-researchers. Congratulations to Michelle and Megan on that award. Just one more time. This has been such an exciting event, and I would like to turn it over to Phil to share any ideas or comments that he might like to share.
Hello, everybody. What a great crowd and great friends. I think Cheryl covered the waterfront of all the people. I don't want to repeat things, but I want to congratulate the fellows and the winners of the Marissa Award today. I see. I want to make one other statement. I see. Susan Fowler in the audience. Susan Fowler was the dean in 2005 when this was created. And is Kathy Misek here? No? Okay. Now, Sid Misek and Susan and Beverly and I got together and we put this program together with a lot of interest, a lot of effort and background, and we're just so proud and so pleased. It's nice to see you here. Yeah, yeah. And Mary Calancis, who succeeded her as dean, and Dean Musa. These are all great people, and what I want to just for a moment tell you that the opportunity that you students here have to not only get fellowships and these awards, but also to get a chance to reach those levels and above as other students have come out of this university, this great university. And that opportunity is something that we're glad and proud of having provided for you. Because I hope and I believe that you're motivated when you hear a lecture like this today, which is cutting edge, that's above my broad pay grade. And I would hope to think that you would make a difference, just as we have made a difference, hopefully, in your lives. And I want to give you an example. My grandson, Bradley Zellinger, the son of Karen and Alan Zellinger, my daughter and son-in-law, went to Michigan, went to Harvard MBA, went to Wall Street, and was very successful. Now, Bradley is the younger brother of Marissa, and he started a company that takes care of, that is for early intervention of autistic children ages 2 through 6. He started 5 years ago. He now has over 20 service centers in 4 states providing these services, and he did that because he was motivated. So sometimes in your education, you get a good education and you learn and the books are good and all that, but the practical application of what you do in life is really what counts. And by the way, I'm one of these people that I learned, and I learned from the books and I did my homework, but I also applied what I learned, and that's the reason I could even be here today. So think about that in your futures. Continue, get motivated, and this university is one of the greatest, and this organization, the College of Education, is doing a fantastic job. And Dr. Ray did an outstanding job. A lot of questions, but that's the future. And thank you very much. Thank you very much.
Wonderful. Well, thank you, Dr. Ray, for a very informative and intriguing lecture, including the applications of AI to support the needs of both children and adults, and to use your own words, in impactful ways. I think we don't want to forget that, as we all get wrapped up into AI. To do this positive impact for humans. And I think it's fair to say that for those of you who might be worried that AI will be replacing your jobs, it sounds like we have a long way to go. So, so here we are. Thank you very much, Phil, for your thoughtful reflections on this important work. We really, truly appreciate your commitment to education, and especially the work in communication disorders. And I would really like to thank all of you for joining us today for the 20th Goldstick Lecture. And please join us for a reception that follows for refreshments and hopefully further conversation and a lot more questions. So thank you again. Thank Phil and your family for the generous support. We're grateful to have you all here today.